In this video, we are going to study Gibbs phenomena. To understand Gibbs phenomena, we need to understand the Fourier coefficients, specifically trigonometric Fourier coefficients of a square wave. So let us take a simple example. So let us say we have a square wave. This is t, and let us have a square wave in this way. So here in the negative direction also we have this particular square wave. So let's say the amplitude of this square wave is a and minus a with 0 and so on. The period is t. Now this is represented as x of t. So already we have solved this example and we have find out its trigonometric Fourier coefficients. So representation of this square wave in trigonometric form of Fourier series is given as x of t equal to summation n equal to odd 4a upon n pi sine of n omega t. So we have already discussed it that whenever we have a square wave and we are representing this square wave in terms of trigonometric Fourier series, we get that square wave is combination of only odd harmonics of sine components. So here we have this particular 4a upon n pi represents the amplitude of this sine wave and n omega t represents the different frequencies, and those are multiples of n. Now if we try to generate a sine wave using this equation, so let us say I'm going to consider single component of sine wave. So let's say this n is equal to 1. So we have only the odd values of n. So if we represent the x of t signal for the value n equal to 1, so it becomes x of t is equal to 4a upon pi sine of omega t. So if we consider only single component and if we draw this particular x of t signal, it won't be a square wave, it will be a simply sine signal. This will be a sine component in this way with the peak amplitude as 4a by pi, and towards negative side it will be minus 4a by pi. Similarly, if we go on increasing this value of n, so let's say we are taking more number of components into it. Let's say we have 4 components. So let's have capital N equal to 4. So 4 components. So small n will have values. So n will have only odd values. So n equal to 1, 3, 5 and 7. So our x of t becomes, so n equal to 1, that is summation of n equal to 1 to 7, but only for odd components, 4a upon n pi sine of n omega t. So this equation becomes now 4a by pi sine of omega t plus 4a upon 3 pi sine of 3 omega t plus 4a by 5 pi sine of 5 omega t plus 4a upon 7 pi sine of 7 omega t. So here we have now addition of 4 sine components, but their frequencies are different. And with this equation, if we add all these 4 sine components and if we try to plot this square wave, we get square wave in this form. So first of all, let me draw the nature of square wave. towards negative side also we have the square components. Okay, so if we try to draw square wave of with 4 components, we get the square wave in this form. So towards negative side also we get such kind of waveform. So here these are called as ripples. So what this Gibbs phenomena suggests that if we give more weightage to the first components of Fourier coefficients and if we neglect the remaining coefficients, we get ripples at point of discontinuity. Means what? See, if you look at the Fourier equation of this square wave, it is given as x of t equal to summation of all the odd harmonics of the sine component. So here this n will have values as 1, 3, 5, 7 and so on up to infinity. So if we add all these components, we get a perfect square wave. But here we have considered n equal to 1. So capital 1 has only one component, so small n will have only one value. So we get, instead of square wave, we get a sine wave. Now next we have assumed that n equal to 4. So we are considering only first 4 components of that summation. And those 4 components are for the value small n equal to 1, 3, 5 and 7. So these are the 4 components. And if we add these sine waves together, we get such kind of a square wave. It is not exactly square wave because square wave has, for the cycle it should have a constant line at positive and negative side. But due to we are assuming or we are assigning more weightage to only first 4 components and we are neglecting the remaining components, that is from let's say 9 to infinity. So we are neglecting those components. Because of this we get ripples at point of discontinuity. Point of discontinuity means what? The square wave is rising at 0, so it is going from negative value to positive value, and again for the next cycle it goes from positive to negative value. So where we have such changes, we get ripples at this point of discontinuities and we do not get a perfect square wave. So this effect is called as Gibbs phenomena and it occurs due to the more weightage assigned to the components, few of the component values and neglecting the remaining values. So this particular ringing effect is called as is because of the Gibbs phenomena. So similarly, if we increase the value of n, so let's say n equal to 20. So if we try to plot the square wave for n equal to 20, we will get a square wave of this nature. So now it will be more like a square wave and the ringing effect is now somewhat reduced. So if we go on increasing the value of n, this ringing effect is more closer to discontinuous nature of the waveform and we get this particular square wave in a proper way. So in this way, if we increase value of this n equal to 50, we get more closer square wave from the Fourier series equation. So this effect is called as Gibbs phenomena.